Hello, welcome back. Today we'll be finishing out 7.3 on the word problems. So we'll start with a geometry problem. We're going to minimize the amount of material needed to construct an open top box. We do have a couple of key features though of said box. So we have, write the key ideas. Open top box. We're going to have two parallel dividers. And the volume that it holds must equal 216 cubic inches. And we want to find the dimensions that will require the least amount of material. All right, so I'll start with a quick sketch. You've seen some of my sketches before, not necessarily works of art. So here is the front of the box, the back of the box, and we'll connect the box up. Lovely, lovely. We have our little cube. And the idea is we also have a pair of dividers in the box as well. So there's one of them. There's one more divider. So two dividers built into the box. So the top is open, and we'll get into our equations. We'll start picking this apart. So here we'll have our width, our length, and our height. So we know the volume has to be 216 in cubic inches. The volume for a rectangular solid is length times width times height, which again is by substitution 216. And what we can do here is basically pick one variable and get it by itself. Arbitrarily, I'll do the length. So the length is 216 over width times height. Or if you like it without the fraction, 216 width to the negative first, height to the negative first. Now that is our constraint equation. The equation we're looking to optimize the surface area, which I'll use a cap S for. So surface area, for starters, we'll do the front, back, and the two dividers. So we have 4 of those pieces, and each one of those is length times height. We'll do the substitution momentarily. Left and right sides, we just have 2 of those, no extra dividers going this way, and those are width times height. Top and bottom, remember we have an open top box, so just the bottom, and that is length times width. Now we can use our substitution. We can replace the length. So our surface area, 4 times, there's our length. Instead, we'll do 216 width to the negative first, height to the negative first, times height, plus 2 times width times height, plus there's another length. Replace it with 216 width to the negative first, height to the negative first, and multiply by width. So we have a little cleanup we can do here. H to the negative first times h is a 1. 1 times anything is that anything. So our surface area is now 864. Width to the negative first. Height's canceled. Plus 2 times width times height. Plus 216. Again, width to the negative first, width to the first will become a 1 when we multiply them, so we just keep the height to the negative first. So this is our output equation. We're looking at one output variable, two input variables, and we're looking to optimize. So this is just applying what we learned last time. So we'll do partial derivatives. So partial with respect to w would be negative 864, w to the negative second from the first term. Second term, h is treated as if it's a constant, so plus 2h. Derivative of w to the first is a 1. And since at the moment w is our variable, h is treated as if it's a constant, that last term drops off. We also have our partial with respect to height. So first term now drops off since there are no heights. Second term, now the height is a variable, width is treated as if it's constant, so we have a 2w. And our last term would be minus 216 h to the negative second. So we can do our second order derivatives as well. So with respect to w both times, we go back to this guy. Negative 864 times negative 2. Negative by negative is a positive. Yeah, let's see. 1728. W to the negative third power. Derivative of the constant is 0. Partial with respect to one of each independent variables. Either this guy with respect to h would be a 2, or this guy with respect to w, also a 2. And finally, our last second order partial, h both times. So 2w drops out, negative by negative is kicking us back over to a positive, so 432, h to the negative third. So we have all of our derivatives. We're looking for the key values, key points. So we're going to take these first derivatives, find out where they're worth 0, and that will give us our point AB to investigate. So our first one, 0, is negative 864 over w squared plus 2h. So we can just get the h by itself. So 864 over w squared is worth 2h. So then h is, we'll cut both sides in half, so 432 over w squared. Then we can use that in our second first order equation, getting rid of our h. So 0 is 2w minus 216 over h squared. So h we can replace. So 0 is 2w minus 216 over h squared. 432, notice, is 216 by 2. And we have w squared as well. So dividing by a fraction, we multiply by the reciprocal, and we'll have to continue that on the next page. Okay, so we had 0 is equal to 2w minus 216 over 2 squared, 216 squared over w to the 4th. All right, so 0, 2w minus, as we said, multiply by the reciprocal, 216 over 1 times w to the 4th over 2 squared by 216 squared. All right, so we can lose one copy of the 216s. So 0 is 2w minus, not an equal, minus w to the 4th over 4 by 216. So 864. All right, so we'll clear the fraction, multiply both sides by 864. So 1728w minus w to the 4th, and we can do a little factoring there. So w 1728 minus w cubed. So w equals 0. We can discard that. With 0 does not really make any sense. So we'll set the other factor to 0 and solve. So we'll just do the cube root of both sides. And w is a nice, neat, pretty 12. That will allow us to find the height and the length as well. So by substitution, we'll flip back to our other page here. So we found the height to be 432 over w squared. So 432 over 144. And we get a nice, neat, pretty integer of 3 out of that guy. And finally, our length. Remember, 216 was length times width times height. We have a width, we have a height. So 216 is length times 12 times 3. So divide both sides by 36. And length is 6. And then the last thing we'll do is prove that that is indeed a minimum. So we'll find our A, B, and C here. So we'll find SWW of 12.3. So SWW 1728 over W cubed. And our W again was 12. So there's our A value, SWH of 12.3. So our other second order derivative, that was always the constant 2. That is our B. And our last second order partial derivative, SHH of 12.3. SHH, recall, was 432 over h cubed. And h is 3 over 3 cubed. So that is 16. That's our C value. So AC minus B squared. So 1 times 16 minus 2 squared. 16 minus 4 is 12. That is greater than 0. So if you'll recall from our theorem number 2, again, you don't have to have theorem number 2 memorized, just be able to put it to work. So AC minus B squared is greater than 0. So we're in either case 1 or 2. We have either a local max or a local min. To finish it off, we find A. A is also greater than 0, which means f of AB is a local min. That's what we're hoping for. So F for the general one, S for this particular one, S of 12.3 is a local min. So the dimensions to minimize material are W equals 12 inches, H equals 3 inches, L equals 6 inches. We have all 3 dimensions, and we've proven that it is indeed a minimum amount of material that we're then using. Okay, so our next word problem, we're going back to selling brand A and brand B again. So leaning on some things that we've already seen. And we'll just kind of summarize what we know. So our demand is X and Y, each in ounces. Price for brand A we called B, brand B we called it Q, each of those in dollars. And the relationship between the two for A, X was 100 minus 5P plus 2Q, and Y was 50 plus 2P minus 5Q. Price, of course, per ounce still, if we're measuring the demand in ounces as well. And basically, okay, you're the store operator. We want to know how we should price each to maximize the revenue. First, we'll talk just real quick about the signs that we see. X is the demand for brand A. P had a negative coefficient here. So as P is increasing, X is decreasing. Higher price for brand A, less of brand A being sold. Also, though, brand A is not the only game in town. Q has a positive coefficient. Q is the price of brand B. As the price of brand B increases, it is going to drive some demand up for brand A. If B is getting more expensive, some customers are going to switch and buy brand A. And notice we have the signs flipped on the other guy. So as price for brand A increases, demand for brand B will increase. Price for brand B increases, demand for brand B decrease. So we're looking to price this out. So we'll look at our revenue function. Revenue is just how much you're selling times how much you're selling it for. So we saw the XP from before, and that's if we only have one brand going. But we also are taking in money from another brand, so we also have plus YQ. Now, I definitely don't want to have 4 variables total for inputs, so I rely on this relationship between them. So my revenue, X, I'll substitute in 100 minus 5P plus 2Q times P. So this whole thing went in for the X. Just don't forget to hang on to your P that was already there. Plus Y, same idea. We're replacing the entirety of Y with, in this case, 50 plus 2P minus 5Q. And then don't forget to multiply by Q that was originally there. So a little cleanup on our revenue function, 100P minus 5P squared plus 2PQ plus 50 times Q plus 2PQ minus 5 times Q squared. We just have a couple of like terms there, 2PQ and 2PQ. So our revenue, negative 5P squared minus 5Q squared plus 100P plus 50Q, and putting our two guys together, plus 4 times PQ. Okay, so this is the function that we're looking now to optimize. So then we get to our partial derivatives. So we have P's and Q's in this guy, so I'll find partial with respect to P to start us off. So first term, negative 10P. Second term is treated as a constant, so that drops out. Third term, P is our independent variable at the moment, so plus 100. Fourth term, treated as a constant. And last term, the 4 and the Q are constants. Derivative of a first power is a 1. 4Q times 1 is just 4Q. Okay, we'll do the partial with respect to Q. First term drops off on us then. So we have negative 10Q. 100P is treated as a constant at the moment. That'll drop off. Derivative of 50Q is plus 50. And derivative of 4PQ now is 4P, since the Q is now being treated as the variable. So there's our first order guys. Then we go to our second order guys. So our second derivative with respect to P each time would be negative 10. Those two drop off. Partial with respect to one of each of the variables. Notice from either one we would have a 4. And our last one with respect to Q both times is a negative 10. So before I even find the price point, I have my A, B, and C, since these 3 are all constants. So this is our A, this is our B, this is our C. And AC minus B squared, negative 10 by negative 10, minus 4 squared, 100 minus 16, 84, greater than 0. A is less than 0, so this is a max. All right. So now to find what that actual point is, so we're taking our first derivative, setting them to 0, and solving that nice pretty little system. So our first one setting to 0, 0 is negative 10P plus 100 plus 4Q. Second one, 0, is negative 10q plus 50 plus 4p. And here, let's kind of get it a little organized there. So 10p minus 4q is 100, together with negative 4p plus 10q is 50. So we're just moving the constants over to one side. If you want to work with smaller numbers, you can factor a 2 out of both of those equations. So 5p minus 2q is worth 50, together with negative 2p plus 5q is worth 25. And then we're just looking to drop a variable. So this is one we can just solve by elimination. All right, so let's drop out our p. So that'll bring row 1 back to how it was. Row 2 will multiply by 5. P's drop out. So 21q is worth 225. So 225 over 21. We have an approximate then, since this is Q, remember, is a price in dollars. So we get 10.7142857, etc., etc., etc. We'll approximate that to be $10.71 per ounce. That's what we'll charge for brand B. So then we want to know what to charge for brand A. We just sub that back into either of these original equations. I am out of room on this page, so we'll have to do that on the next page here. So we'll just do the 5p minus 2q is 50. And recall Q, since we obviously can't charge the customer 0.7142857, we'll call it $10.71. So 5p minus 2 by 1071 is worth 50, and then you're just solving a linear equation. So 50 plus 2142. So 5p is worth 7142, and cut both sides by a fifth. And 14.284. Again, we can't charge fractions of a penny, so we'll round that off. So to maximize revenue, the store should charge $14.28 per ounce for brand A and $10.71 for brand B. Now, if you're off by a penny or two on this, it just means that the author, or more likely the author's grad assistant, solved for a different variable first and rounded at a slightly different spot. If you can get this far, I'm very content with that. Okay, so that should give you enough ammo to finish the previous assignment from, again, this is 7.3. If you have questions, please feel free to reach out to me. Otherwise, stay safe out there, and I will see you next time.